Okay, 6.3. I'm gonna pop some of these out. I did draw some pictures on this one. This kind of stuff is really a little difficult to explain, and I have stuff I go over in class, but it's kind of hard to do that on video. So this first section is the beginning of the unit circle, and hopefully y'all remember that you label these quadrants counterclockwise. 1, 2, 3, and 4. Now, because this is more interesting than pre-calculus is, and I'm not going to make anybody guess because I have no feedback, but the circle is labeled in a counterclockwise fashion because most people are right-handed. Now, I'm going to turn around here. If I were standing at the board and I took my hand to draw on the board behind me, most people are right-handed, and most people will grab that marker and commence to sweep in a counterclockwise fashion. That's why, oops, let me turn that down. That's why we do that stuff in a counterclockwise fashion. Western culture won the war on how to draw a circle. Now, Eastern cultures, you draw circles in a clockwise fashion. It's very stylized. I'm assuming you guys have seen, if nothing else, some James Bond movies where they show some of the stylized painting. But they didn't win the publicity war. We did. You swing around in that counterclockwise fashion. That is why the circle is counted in that fashion. That's how people draw in our culture. And like I said, we won that war. So, counting in that direction means counterclockwise, starting at that x-axis, the one that's so right here would be normally on the board when I was turning around to you guys. This is 0 degrees, and you start counting all the way around. Here's 180. Every right angle is 90 degrees. The entire circle is 360 degrees, or 2 pi. So, but this first setup is all degrees. So, starting here, 0, 90, 180, 270, 360, and you can just keep on looping around. All you're doing is adding. So 360 plus another 90 is what? 450, plus another 90 is 540, plus another 90 is 630. And when you label these angles, these degrees, all you're doing is counting roughly to where they are. They don't have to be exact. I label the quadrants. If you really wanted to practice, I would sketch out a circle and just draw them in little dots on there, kind of get the hang of how that circle works. That unit circle, and this is an engineering or a manufacturing statement, the fact that that circle loops and loops and loops constantly, so I'll do this way for you guys on the camera, is how you make a complicated thing simple. You work with it on the first loop, and then you continue to loop it. It's just like a spring. That first twist to make a spring is easy. It's as you keep twisting, it gets harder and harder and harder. You're going to need a vise, you're going to need pliers, because you're getting more and more tension built into all of those layers. Math and nature and engineering is a lot like that. The first step is easy, but when you're up to the 15th floor, suddenly things are hard. Even though the mechanics are the same, it's become hard because it's become so large. The unit circle is one unit. It's simple. It's easy. You can make your plans. You can work out your problem without all the extra stuff that gets into it. And then once you have that basic solution, then each little layer adds a complication that you can deal with as you get to it. That makes a problem solvable. Math majors do not market themselves as math majors. They're marketed as problem solvers, facilitators, troubleshooters. Because what you're supposed to learn in this class, if you're not a math major, is that things are not always as complicated as they seem. That you can take things apart and deal with each little piece of the problem, and then go back and put the whole thing together for a total solution. That way you don't look at a problem and think, well, this just can't be done. Because most of the time it can be done, but you need to change your way of thinking, change the way it's laid out, change its format, change the language you're using, because that's part of what trig is. We're going to do the same thing over and over in about 5 different languages. This is the first one, the unit circle language. The triangle, the sine, the cosine. There are several more that are really accomplishing the exact same thing, just in a different language, because some things are easier in one language than the other. Seems to me that Latin has 20 or more words for love, and the English language has 3, something like that. That's why. Some things are easier in another language than they are in the one you're in. Okay, so let's put this back. Now that I've laid that out sort of, the reason I laid that out is because you're taking that unit circle and putting it onto a language you already know. That Cartesian coordinate plane, that little XY axis, the graphing and all that crap from algebra that you had forever. This works the same way. When somebody gives you a point that says positive 5, negative 12, if you had that graph behind me, you would start at the 0. Remember, do horizontal first. Positive 5, negative 12. Whatever point you hit right there, if you drew a circle through that point centered at the origin, that's going to make the circle you're talking about, and you can slap that triangle in there. Now, my triangles in my pictures are not necessarily done exactly in the right way. I try to make sure they're lined up so that the little bitty end is at the origin, and it shows the way the triangle sweeps out because it makes it easier. Now, but that layout, it's irrelevant to doing it. It's still the same setup. Once you get your triangle on there, once you talk about which angle you're talking about, opposite and adjacent are labeled the same way. The hypotenuse is exactly the same. Treat your x-coordinate as your adjacent side. Treat your y-coordinate as your opposite side, and things will be fine. You don't even need a picture once you do that. So I did 25, 26, 27. Got all the layout in there. You can just redo the problems as you see fit to get the hang of it. Like I said, all the little tools for doing this you already have. The only thing that's changed is the way you're using them. Now, here's one of the problems where I said there's a mistake in it and I left it. On number 30, oh, this is, yeah, on 6.3. On number 30, let's see if I remember what I did. 1, 4, 1, 4, 16. I wrote a mistake on it. I wonder what I did. Maybe the problem is wrong. 6.3. 6.2. Number 30. Oh, I know what I did. I left the negative off. I have somehow, it says that the line is 4x plus y, equals 0, but we're interested in the part of the line that's in quadrant 2. The way I sketched that out there, I was just rolling through these problems and doing them. I didn't draw it that way. Quadrant 2 means that line should have been tipped the other direction. It should not have been 1, 4. It should have been negative 1, 4. So when I graphed that line to make my picture, I screwed it up. Now, I'm happy with either answer if this one is on the test. Usually I make sure the ones with mistakes are on the test. But if you want to practice how much you've actually kind of figured out, don't just copy this one. Try to fix my mistake. It's just a negative sign. Other than that, it should be fairly straightforward. The only difference is you'll have some more negatives in here. If you can figure that out, that is one more step in understanding what we're doing, because you guys have the tools. You've had the tools when you walked in the classroom. All we're doing is rearranging them. And most issues that you're going to have from here on out, if you really do a lot of math, is nitpicky stuff like this. So number 30 on the notes has a mistake in it. I told you what the mistake is. If you catch it, fine. If not, your life will probably go on. It'll be all right. Let's see. That's that section. Then we get to number 39. Okay. I'm going to stop and do this last page on its own video because I didn't really explain this in the notes.